Well, welcome everybody to Wednesday Night Lab. I'm Tom Zinnan. I work here at the UW-Madison Biotechnology Center. I also work for the Division of Extension, Wisconsin 4-H. And on behalf of those folks and our other co-organizers, PBS Wisconsin, the Wisconsin Alumni Association, and the UW-Madison Science Alliance, thanks again for coming to Wednesday Night at the Lab. We do this every Wednesday night, 50 times a year. Tonight, it's my pleasure to introduce to you Keith Levin. He's a new professor in the Department of Statistics, and he's also across the street at the Wisconsin Institute for Discovery. He's going to talk with us about networks, the science of interconnected systems. And now I get to ask him our favorite 5 questions. Keith, where were you born?
I was born in Boston, Massachusetts.
And where'd you go to high school?
Canton High School, south of Boston.
All right. Isn't there a Hall of Fame in Canton?
Wrong Canton.
Yeah, I know.
Yeah. Dunkin' Donuts corporate headquarters, though, so we got that going for us.
And then where'd you go to undergrad and what'd you study?
I went to undergrad at Northeastern University. This is actually all on this slide. I'll just skip to it.
I know, but I get to ask you anyway.
I went to Northeastern University for undergrad. I studied linguistics and psychology, and I minored in computer science because a boy's got to eat.
What part of linguistics did you focus on?
I studied a lot of semantics and syntax and promptly forgot it all. And I became obsessed with phonetics, but I was bad at it. So.
Well, if only I could pronounce phonetics.
Okay.
And then where did you go for your advanced degrees?
I did my PhD and a master's along the way at Johns Hopkins University in Baltimore in computer science. Very good.
And did you do any postdocs or anything like that?
I did. I was a postdoc for 3 years in the statistics department at University of Michigan.
Very good. And then did you come here?
Yes.
What year did you arrive here?
I started here in 2020, in the midst of the pandemic.
Good. And then you were here last fall to tune into some of you came to one of the Wednesday nights of the lab?
I was, yeah. I've been in person to a few of these, and I've watched a bunch online as well.
Great. I really appreciate you volunteering to share
I'm happy to do it. It's my pleasure to be here.
Networks, man. It's not just ABC anymore. And that's the Australian Broadcasting Corporation. Thank you. So would you please join me in welcoming Keith Levin to Wednesday Night at the Lab.
Thanks so much. Thank you, Tom, for the kind introduction. Thank you all for being here. Before I really dive into things here, I did want to kind of expand on Tom's point. So I started as faculty here just over a little less than 2 years ago. In the depth of the pandemic, I moved here in May and started officially in July. And I didn't even have an office my first year as faculty here. And so Wednesday Night at the Lab has been a really great way to see what folks are working on in a time when I literally didn't even really have a campus to come to. So it really is my pleasure to give back a little bit and contribute a talk. And it's lovely to see all of you here. And I will give a shout out to all the folks on Zoom. And I'll even take a moment to check in with the people on Zoom that you can hear me properly, because I have been on the Zoom before and the audio was broken. So Zoom folks, this is your time to yell about it if there's a problem. But I'm getting a thumbs up from the sound people, so that's good. Anyhow, you already got most of this information already. My background is somewhat, let's say, non-traditional. My undergraduate degree is in linguistics and psychology. I loved cognitive science. And in the course of studying that, I found out that really the part of cognitive science I was best at was the computing and statistics. And so here I am. I spent a bit of time between undergrad and my graduate work as a data analyst doing some statistics and some software engineering at BBN Technologies. They're a old school engineering firm just north of Boston, and put a pin in that name because they'll come up again in a few slides. So after some graduate work and a few years at a postdoc on the wrong side of Lake Michigan, I landed here, like I mentioned, in 2020. I'm an assistant professor here. Most of my teaching focuses on teaching our young statisticians how to use computers. So things like, if you've heard of R, the computing language, I teach a couple of data science courses at both the master's and undergraduate level. And then my research, which I'll talk about a little bit today, focuses on developing statistical methods for analyzing network-valued data. And if you don't know what network data is, that's okay. That's the point of today's talk. So you can safely wait to find out. I work a lot on methodology and theory, meaning I spend a lot of time scribbling on paper and squinting at screens, but I also spend a lot of time motivating that work by applications in the sciences. Most of my time is spent thinking about neuroscience. I used to do a lot of speech recognition, less and less these days. And I'm also increasingly interested in microbiomics, and I'll talk a little bit about some of that stuff in the last third of today's talk. So, first and foremost, what is a network? In a very short form, a network describes a system of interacting entities. So we have actors or objects of some kind out there in the world, and certain pairs of those actors or entities interact with one another. We depict a network by drawing a bunch of dots with lines between them. So, for example, we might have a collection of 5 people, some of whom are friends. So our actors are the entities Alice, Bob, Carol, Dave, and Eve, and pairs of them interact by, say, being friends. For those pairs of agents or entities who interact, we'll draw a line between them. Okay? And so more formally, we call these dots, our actors, the vertices of our network. Okay? The singular is vertex. And pairs of these vertices, pairs of these entities who interact are said to form an edge. So the name for these lines between vertices are edges. Okay? You will sometimes see this kind of a structure called a graph, especially in the computer science literature. There are sticklers out there who will use these two terms to mean slightly different things. You'll hear me slip up and say graph when I really, like today, I'd like to just use the word network to avoid confusion. But this is the kind of thing where you go out and read about this and you'll be like, what the heck is the difference? And don't worry about it. So hopefully the example of networks that's most familiar to most of us here is something like a social network. I mean, there was even a movie named after them not that long ago, right? So let's think about Facebook. There we have people who are users of Facebook, and certain pairs of those people, certain pairs of those users are friends. So we might depict the Facebook network by creating a vertex for each of our users. Let's imagine Facebook only has 5 people because I don't have enough room on the slide. Right? So Alice, Bob, Carol, Dave, and Eve are all users of Facebook. We give each of them a vertex. Pairs of them that are friends get a line between them. They form edges. So in this case, our vertices in our network represent users of Facebook. The edges encode which pairs of users are friends with one another. Let's look at a slightly less obvious example and think about the World Wide Web. Just as a refresher, the World Wide Web describes the collection of all websites that are out there in the world. It resides on the internet, but the internet and the World Wide Web are not the same thing. We'll talk about the internet on the next slide. So we can create a network whose vertices correspond to websites by, well, creating a vertex for every website out there, wikipedia.org, my home department's webpage, the journal Science's webpage, and so on. And certain web pages link to others, right? Like you can go to Wikipedia and click around a bit and find a link from Wikipedia to the statistics department website or to the science journal website, and so on. So for pairs of these websites that link one to another, we could say that they form an edge together. Okay, so we can represent the network of all web pages with their hyperlink structure according to a network. Let's see another example. This one, the actual physical internet, as distinct from the World Wide Web. So the internet with a capital I refers to the collection of all computers in the world that are networked to one another. So this computer that I'm displaying these slides from is on the internet. Your phone is on the internet. Any server you ever ping for a website is on the internet. It's just the collection of all computers, pairs of which can interact with one another by sending information over a wire or a satellite connection, things like that. The internet as we know it today grew out of a government project in the 60s and 70s called ARPANET. And this is a image of that network early on in like 1970-ish, at a time when there were only 13 computers on the internet. So all of Facebook would have been 13 people just like yelling at each other, I guess. So I don't know how easily you can read this, but we had computers at places like University of Utah, Stanford, Case Western, Carnegie Mellon, a little place called BBN Technologies, 50 years before I worked there, or 40 years before I worked there. So each of these vertices in this little network corresponds to a computer like sitting in a closet somewhere at one of these universities or research labs. Okay? And then the edges that join certain pairs of these vertices corresponds to wired connections. I believe at this time it was all by wire. Maybe some of these were satellite. I'm not a historian of the internet, unfortunately. That sounds like a cool job that someone ought to have, though. Okay, so now we can represent the internet, the physical internet, as it exists, as a collection of vertices that represent the computers on that network, and the edges in this network would represent pairs of those computers that can communicate directly over wire or satellite, something like that. Hopefully by now I'm convincing you that networks are everywhere, but I'm going to keep convincing you for at least another 3 slides until our eyes are like really bleeding over this. Let's look at something a little less obvious. The human microbiome refers to the collection of bacteria that live in our gut. Everyone has one, and it's a little gross to think about, but you have a whole ecosystem crawling around inside of you. We can look at different people's gut microbiomes and look at what species of bacteria tend to live there and in what kind of abundance. And we can look over lots of different people in one of these studies what pairs of these bacteria tend to be more or less common. And are there certain bacteria that tend to show up together, or tend to, if one's present, the other's not present, some kind of relation like that. We call that correlation in statistics, just a measure of how much do these two things vary with one another. And we can say for pairs of species of bacteria that seem to have high correlation, we can form a network where edges encode which pairs of these bacteria seem to co-occur a lot or correlate with one another strongly. Okay, so in this case, our network has vertices corresponding to gross-sounding bacteria like Clostridium and Caloromator, and the edges encode which pairs of these bacteria tend to correlate with one another in the human gut microbiome. So that correlation is measured by looking at lots of different people's gut microbiomes and just measuring how often do these two things show up together, essentially. So this network that I drew for you is adapted from a figure in a paper by Claudia Solis-Lemus and one of her students. So this is work actually right here from UW-Madison, and I'm pretty sure Claudia actually gave Wednesday night at the lab talk like just before the pandemic, I think. Someone has to go to the archives and check, but just a nice little reference to another Wednesday night at the lab speaker. Okay, so if you go to that paper, this network looks a lot cooler there, but it doesn't like blow up to the slide very, very naturally. Let's look at an example near and dear to my own heart. This comes from neuroscience. So the neuroscientists say Connectome, but what they really mean by that is just a brain network. So this is a way of taking a brain, usually from a human, but can be from really any organism, breaking that brain up into sections that we call regions of interest. So these are kind of, think of these as chunks of brain, and measuring how much pairs of those chunks of brain seem to work together in people sitting in an MRI machine. So we can form a network whose vertices correspond to these brain regions, these chunks of brain, and the edges encode which pairs of these brain regions seem to work hard at the same time doing certain tasks. So the way this works at a very high level is subjects lie down in an MRI machine, we take a picture of their brain several times over time, and measure what parts of the brain are using oxygen at the same time. Right? So what part of the brain is consuming oxygen at any given time is a good proxy for what parts of the brain are working hard. So if you're, I don't know, if they make you do math problems in the MRI machine, certain parts of the brain consume more oxygen. Okay, and we can look at what parts of the brain tend to consume a lot of oxygen at the same time. That suggests that those parts of the brain are involved in the same task. Right? So we can ask what pairs of these brain regions seem to be interacting closely. Those pairs will get an edge between them. One last example, and then we'll shift gears. I can't imagine why, but some people might like to study how diseases spread in a population. Not at all relevant. So one reason why social networks and network structures in general are important is not just because, well, they look cool and there's like interesting stuff going on, but actually you might care about the processes that happen on those networks. So we can form, say, a social network where, again, our vertices are our old friends Alice, Bob, Carol, Dave, and Eve. But now maybe edges encode which pairs of these people interact closely in their daily life. So maybe, I don't know, Bob and Dave work together, Alice, Bob, and Carol are roommates, I don't know, right? And the question might be, if one of these people gets sick, how might that disease spread through the network, right? And if we understand those kinds of dynamics, that can inform things like vaccine strategies, right? Who should get a vaccine first in a population? How should we try to distribute vaccines? If we understand how diseases spread on a network like this, We can better prepare ourselves for pandemics. Well, the next one anyway. So I hope that at this point I've convinced you that networks are everywhere, and you will leave this room today, like everything you see for the rest of your life, you're going to be like, wow, that's probably described by a network, and you'll be correct because they're everywhere. I want to spend the next chunk of this talk explaining why it's not just like, oh, well, we can draw these cool pictures and they're fun to look at, but networks that we observe in lots of different scientific domains tend to display some properties across these domains that are kind of strikingly, well, it's surprising that we should see these properties show up again and again. So I'm going to talk about 3 properties. They have special names. They're on the slide, but I have no expectation that you know what these mean yet. I'm going to tell you. That these 3 properties are observed in networks arising in vastly different areas of science. So we go and collect an ecology data set like a food web, and we look at a connectome, and we look at a social network, and we look at trade networks and economics. And all of these networks seem to quite often exhibit these 3 phenomena that I'll talk about in the next few slides. Okay? So this kind of hints at there being some kind of a bizarre, explaining why all of these different domains display these same kinds of properties is an interesting problem. So the first of these properties is referred to as power law degree distributions. You'll also see this in the literature called a scale-free network. To understand what this means, well, first we need to know what the heck is a degree. The degree of a vertex in a network is just the number of friends it has, so the number of edges it participates in, or the number of neighbors it has. Right? So just a very simple example, you're going to be so sick of this, if you're not already, you're going to be so sick of this one network by the end of this talk. Right? So here's our social network. The degree of each of these vertices is just the number of edges it participates in. So the number of neighbors it has is a social network, the number of friends it has. Okay? So Alice has 2 friends, Bob and Carol. Alice's degree is 2. Bob has 3 friends, Alice, Carol, Dave. Bob's degree is 3. Okay, you all know how to count. I'm going to stop there. Right? Okay, I don't know. Last one. Eve has 1 friend. Dave. Eve's degree is 1. Poor Eve. Okay, so for any network, we can just make this list. Right? Every vertex has its degree, and then we can make a histogram of those degrees. Here's that histogram for Twitter like 10 years ago. So this is very out-of-date data, but it was the first thing I found when I started Googling. I'm like, where the heck is that Twitter data? And it's fine. This same pattern shows up now, I promise. So let's unpack this plot, because, well, 1, it's a little hard to read on this projector, and 2, it's not obvious at first what's going on. The x-axis here is a number of followers, which, again, in this case, just means like your degree. How many friends do you have? The y-axis is frequency in percentage. So what percentage of users have this particular degree? So way here at the left, what percentage of Twitter users have 1 friend, have 1 follower? What percentage of Twitter users have degree 1? Like 20%. Like 1/5 of Twitter users have 1 follower, have 1 friend. So if you have more than that, you're already doing okay. But I don't know. I don't have a Twitter, and so I guess I lose this game, especially. Like I'm over here, I guess. Just looking at this plot, you see that the vast majority of Twitter users have fewer than 500, degree lower than 500, fewer than 500 followers. Okay? But there are users way out here at the far end of this distribution, right? So there are lots and lots of users who have very few followers, but then there's, okay, this was 2013, and I think, like Justin Bieber, I think, was the most followed person on Twitter at the time. This is when I was in grad school, and there was like a running joke that Justin Bieber is like way out here somewhere. So like Justin Bieber, Barack Obama, there are a handful of people with millions of Twitter followers, right? But most people on Twitter are down here. So we have this very skewed distribution, right? Really heavy right tail, we call it. Distributions that look like this are called power laws. Power law has a more rigorous meaning than that, than just simply right skewed. But for the purposes of our talk today, this kind of a pattern where most people have very little and a handful of users or vertices account for a handful of very large degrees, that's a power law. Okay. This kind of phenomenon was first studied by an English physicist, Derek de Solla Price. He looked at the network formed by scientific papers, being the vertices, and edges are citations. So how many citations do different scientific papers have? So this is that same plot we saw on the previous slide. This time, the x-axis is the number of citations a paper gets. The y-axis is that frequency again. One important thing to note, the y-axis now is on a log scale. I don't mean to scare anyone back to like high school math, right? But so now 1 unit of increase on the y-axis means multiplying by 10. Okay, I promise this is the hardest math we're going to do tonight. I promise. Okay, so this is not like you expect to see this kind of crazy drop-off. You don't see it. That's because we've kind of crunched the y-axis down a lot. Okay, let's unpack this. 75% of scientific papers in this collection, and these are papers from like 1961, I think, give or take. Okay? 75% of those papers had 1 citation. It's kind of a bummer. I have some papers with 1 citation. What are you going to do? What is that? Maybe we'll call it 15% of papers had 2 citations. 8, I don't know, less than 10% of papers had 3 citations, and so on. Now we go way out here to papers with 18, 19, 20 citations. But maybe a little more than 0.01% of all papers have more than 18-ish citations. Okay? So the vast majority of papers have very small degree, right? Very few friends, very few citations. A handful of papers, like 0.02% we'll call it, have a very high degree. Okay? Really extreme skew in this distribution. Okay? That's the power law. Now, I've shown you 2 networks that arise from kind of social phenomena, right? People interacting with one another. But here are some examples where it's not so clear that this is just a social phenomenon, right? You can take any network and make this plot, and you'll see the same kind of, not literally any network. You can cook up networks where this doesn't happen. The vast majority of networks that we go out and see in the world display something like this phenomenon. So here are 3 examples. I apologize, I've changed things on you again. Now both axes are on the log scale. I was trying to like kind of ease you into it with, there's no log, now there's 1. Okay. So the cool thing about power laws, though, is that when you plot them on a log-log scale, so both the x-axis and y-axis are scrunched in this way so that 1 unit of change is it's like a power of 10, power laws look linear. That's actually like the almost definitional way we talk about them. Okay? So you take the degree, the histogram of degrees, and plot it on this log-log scale, and you see these very nice straight lines show up. This happens whether you look at social networks like Twitter, you look at the World Wide Web link structure, you look at the US power grid. Why should this be the case? It's not obvious at first. Now, there's an entire literature explaining why this might happen, and in fact, phenomena like this have been observed elsewhere, not just in networks. You may have seen things like this referred to as things like the Pareto principle or the 80-20 rule. That's a phenomenon in the study of wealth distribution, where 20% of people own something like 80% of the wealth in a society. This is broadly observed in Western countries with some variance. So there are explanations for why these things might happen mechanistically, but it's quite remarkable that we see this happen in a wide variety of domains. Let's talk about another striking property of networks out in the wild. Networks are locally dense and globally sparse. What does that mean? Let's take each of those terms one at a time. Globally sparse. This is best illustrated by just thinking about the global social network. So let's think about the network where every person in the entire world is a vertex, and pairs of people who are friends form an edge. Let's pick any 2 people at random in the world. What is the probability that they are friends? This isn't actually a test question. Like, I don't know the answer either. But it's tiny, right? I mean, vanishingly, like, I think I like my odds of winning the lottery better, I think. Now, different question, but similar. Pick 2 of your friends at random. What's the probability that they are friends? It's not 100% for sure, right? I mean, like, you have friends from work, from your hobbies, from school, who knows, right? But certainly it's higher than the base rate of pick 2 people at random from the whole world. So when I look at the entire social network as a whole, most of the edges that could be there aren't. The network is globally sparse. When I look at the whole network, it looks very sparse, meaning there are very few edges there. But if I look at the local neighborhood of any one vertex, I look at one vertex and look at their neighbors, look at their friends friends tend to be friends with each other. Not all the time, right? But probabilistically, more often than that background base rate of just picking 2 people at random. Okay. Let's get a picture of that. So this global sparsity phenomenon just arises from the fact that there are a lot of possible friendships in a collection of n people when n is big. Okay. I promised that the log was the hardest math we're going to do, and that was only a lie if you like algebra even less than logarithms. So, so among n people, how many ways are there to pick 2 people to be friends? The answer, my cursor's in the way of the answer. The answer is n times n minus 1 divided by 2. That number actually has a name. It's n choose 2. It counts the number of ways to pick 2 things out of a collection of n objects. Okay? So when n is 10, this is 45. There are 45 possible friendships in a group of 10 people. So already, if you're at a cocktail party with 9 other people, there's like a lot of pairings of friends. Right? So in a group of n people on the x-axis, here's how that number grows. It grows quadratically. That's that kind of curve shape. Grows quite fast with n. Right? So if we look at the entire planet, 7 billion and change people, there's something like 5 times 10 to the 19, right? 5 followed by 19 zeros. I don't even know how many billions that is. I stopped to count and gave up. Possible friendships. Quite a large number. How many of those possible friendships are actually in existence? Certainly a vanishingly small proportion of that, which is kind of sad when you think about it. So there are a lot of possible edges that could be there in our global social network, right? But in practice, most of them are not there. Global sparsity. On the other hand, when we look at the local neighborhood of a vertex, meaning start at someone, maybe picked at random, and look at their friends, many of their friends are friends. You can sort of see an example of this on this network that I've shown here. So this is a network whose vertices are blogs, and edges correspond to blogs linking to one another. So if one blog lists another blog, and it's like list of favorite blogs or something like that. And I was afraid this would happen, that this would be a little too hard to see on the projector. But if you can go to this website, these slides will be available online, is my understanding, and play around with this and zoom in and see, like pick out a vertex, look at its neighbors, you'll notice that its neighbors do tend to be linking to one another more often than the base rate. Like if you just pick 2 of these at random, they're almost never friends. Okay, that's local sparsity. If I look at one of these guys and look at its neighbors, they tend to be friends more often than the background rate. The interesting thing is that these locally dense, local neighborhoods of vertices often correspond to communities in the sense of vertices that behave similarly or sort of like the same things or talk to one another or play a similar role. And a central task in network analysis is often identifying those vertices because they often hint at something going on. So a nice example from research happening right here at the UW. Is that me? Oh. My worst nightmare is that I'll be giving a talk and then like FaceTime goes off on my computer. That is not an invitation for my friends to call me right now. Right, where was I? So work happening right here at University of Wisconsin-Madison by my friend and colleague Carl Rowe uses these kinds of ideas to identify groups of like-minded individuals on Twitter and track kind of what's changing in the public attention, so to speak, over time. So Carl and his lab identified 24 groups of these kind of locally dense communities they call flocks, and they built a tool called the murmuration. Murmuration is the word for like a flock of birds that all kind of follow each other and make crazy patterns in the sky. Yeah, cool stuff. They built this tool called murmuration that explores how those flocks and their conversations change over time. So you've had, there's a bunch of people who are like reporters on Wall Street, and what are they talking about? Like, what's the big finance news this week, kind of thing. Right? So these local communities, these locally dense groups of vertices, often hint at groups that are somehow acting together or share an interest or are functionally grouped. And identifying those groups can tell us a lot about the system under study. Okay, one more interesting network phenomenon. This is called the small world phenomenon, probably known to many of you just by a different name. So this was first identified by Frigyes Karinthy And I'm sorry to any of the Hungarian speakers in the audience. I did my best. Like I said, I liked phonetics but was bad at it. So, okay. Karanti was a Hungarian writer. In his short story called Chains in the English translation, he talks about a parlor game where people say, like, let's, how many acquaintanceship hops would it take to get from me to some random person out there in the world? Right? So pick someone somewhere out of the, okay, at the time, 1.5 billion people on Earth. How many acquaintanceships do I need to jump through to get to them? Like, I may not know Mr. X personally, but I know someone who knows someone who knows someone who knows Mr. X. A similar idea was explored in the play 6 Degrees of Separation by John Gare. That name may be familiar to you. That was sort of the pop science name for this phenomenon. That play explored a similar idea. Again, the idea being I can find a chain from myself to anyone else in the world via 6 of these acquaintanceships. Right? A chain of 6. I know someone who knows someone who knows someone who knows someone who knows the president, kind of thing. This was probably made most famous in the mid-2000s by the parlor game 6 Degrees of Kevin Bacon. Rhymes with separation, I guess, if you force it. Right, so that's a game where you pick any actor or actress in Hollywood and try to connect them to Kevin Bacon via edges that correspond to working on the same movie together. Right? So actor X worked on movie A with actress Y, who worked on movie B with actor Z, and so on, connecting to Kevin Bacon. And the game was to do this in 6 hops. And in fact, there was a networks researcher who worked this out and managed to find someone where it took 7 hops. And they worked on like a Soviet film from the 1920s. Like, that's how hard it was to find someone who wasn't 6 hops away from Kevin Bacon. So this had been actually studied in scientific journals, not just by like people on the internet playing around with Kevin Bacon. Stanley Milgram, a famous social psychologist who was at Harvard, actually famous for a different experiment, the Milgram Experiment, which we don't have time to talk about. But Milgram tried to study this phenomenon. So he gave people a token and said, here's the name of another person, which presumably they didn't know. They didn't know the person. And their instructions were, mail this token to someone else with the instructions to mail it to someone else with the goal of eventually getting this token to this target person. Okay? So again, the idea is one person gets a token, their instructions are to mail it to a friend or acquaintance, trying to get that token closer, whatever that means, to a target person. And Milgram tracked how long were these chains that resulted in getting this token from the starting person to the target. Okay, so here's a plot of the length of those chains. And indeed, many of them were like about length 6. Okay, so that's where that 6 degrees of separation thing comes from. But indeed, it's quite striking, right? So there were, I don't know how many millions of people in the US at the time, but you could get from someone in Nebraska to someone in New England in 10 hops. Right? Quite remarkable. And at a time when we didn't have the internet. I mean, we had ARPANET, but it was 5 computers. Now, this shows up well beyond social networks. We look at connectomes, we look at economic networks, like trade networks, all these kinds of things. We see these short paths, right? Small world phenomenon. Any pair of vertices can be connected by a short chain. But even crazier is that this shows up even in completely random networks. So let's play a game. Let's make a random network. We'll start with a set of vertices. And for every pair of vertices, we'll just flip a coin. If the coin lands heads, we'll put an edge between those two vertices. If it lands tails, we won't. Okay. Now, look at the resulting random thing. There's a bunch of vertices. Certain pairs of them form edges together. And let's look at whether any 2 of these vertices can be connected via a short chain. And the answer is yes. So even random networks display the small world property. Now, putting this notion of what does it mean to be a small world network on formal mathematical footing is not to be done in this talk, right? But it can be done, and you can show that the length of this shortest path, as the number of vertices grows, the length of that the diameter of the world, so to speak, right? The length by which you need to connect any 2 vertices, right, grows very slowly as the number of vertices grows. Okay. So in the time we have left, I want to pivot a little bit and talk about some of my own work here and talk a bit about statistical network analysis, which is my own research area. So hopefully at this point in the talk, I've convinced you that networks are everywhere, that they have some kind of mysterious properties, and that it might be worth studying them to understand why those properties arise and when those properties arise. Right? Is it always the case that any network I go look at is power law, has power law degrees? Do we always see the small world phenomenon, and so on? So the first problem that we have when we try to ask statistical questions about networks is that networks are really different from classical statistical data. So in classical statistics, we have a lot of work that's been done to kind of work out how to write down statistical models, how to do inference, right, how to answer scientific questions about a certain kind of data. Data where you can kind of draw histograms, things like that. Things that are nice and easy to think about. Networks are complicated, and it's much harder to write down statistical models for them. But the people in the sciences who are collecting this network value data have scientific questions that they want to answer. And so we need to develop statistical tools for answering those questions. That's the focus of my own work. Right? Said in the very glib way, I work on statistical methods for network data, developing network analogs of classical statistical techniques. So take any tool from the statistics textbook that scientists like to use, develop a network analog of it, something that works for network data. So I want to talk about just one such statistical problem that arises. So, sad fact about the world. There is a true friendship network out there. But when we go and look on Facebook, we don't see it. We see the Facebook network. There are people who are friends in real life who are not friends on Facebook, and there are people who are not friends in real life who are friends on Facebook. And I'm sure you can come up with examples from your own life. Right? So there is some true network out there that we might like to see, that we'd like to study, but we usually don't get to see it. We see a noisy version of it. Right? Maybe certain people don't report that they are friends, or in the case of brain networks, we can only noisily measure the strength of association between certain brain regions. Right? So the thing that we actually observe is kind of like the true network subject to some noise. Right? And so the question is, can we recover that true network? Can we remove the noise from the thing that we measured and get a better guess at what that true structure was that we didn't get to see? One way to think about this is to make a bit of an assumption and say, well, I'm going to assume that the true network is in some sense kind of a simpler, smoother, lower dimensional structure. Okay? And what exactly that lower dimensional thing means, don't worry about it too much. Just think simpler structure. But the thing that I measure is that simpler structure subject to a bunch of noise. Okay? So every edge is like adding some noise to this structure. There's an analogy here with linear regression. Even if you've never seen linear regression before, you're still going to follow this, so don't worry. Here's data we might collect out there in the real world. Right? The blue points. So I make some measurements of x comma y, whatever x and y might be. And if I just look at these points, it looks like there's a lot of noise. There's a lot of complicated stuff going on. Right? There's just like a lot of up and down in the signal. It's not clear that anything, there's just points bouncing all around. But a different way to view this data is that there's a trend given by the red line, and all I got to see was this trend plus a bunch of kind of staticky noise bouncing around. Right? And so what we'd like to do is take this noisy data, the blue points, and smooth it out to recover this nice simple structure, the straight line. Okay? Kind of think of this as like there's a picture on the TV and there's been a bunch of static added to it, and we'd like to kind of get rid of the static, smooth the image out. Right? That's kind of what we'd like to do. Okay? So the network analog is the same idea. Think of the network that we observed as being some smooth, simple structure that's just had some noise added to it. And if only we could kind of smooth out that static, we'd recover a nice, simple structure that we can think about. Okay? So again, in cartoon form, it looks something like this. We see our noisy network, and smoothing it in this case essentially means taking for every edge, getting a probability that tells us how confident are we that there is really an edge between these two vertices. Right? So we took this thing that's every edge is either there or not. It's a binary signal. And we smoothed it out into a bunch of probabilities. Okay? The nice thing here is that this smoother, simpler structure actually lets us do something stronger. We can take the vertices in our network and put each of them in nice, simple Euclidean space, just a point, say, in the plane. Why is that better? Because now you think, like, I've turned a network into geometry, and I also didn't like geometry in high school, so. But here's the thing. The best mathematician is the lazy one, because we don't know that much about modeling and doing statistics for networks, but we have like a century of statistics for dealing with this stuff. So what this whole idea allows us to do is take these complicated and very kind of scary objects, networks, and turn them into geometry. And like, we have textbooks that tell us how to do geometry. We can do statistics on these things. In particular, having that geometric structure, being able to map each vertex to a point in space, lets us do things like compare networks. So I can, for example, take schizophrenic patients and healthy patients, get all of their brain networks, and compare them. Right? So we can apply this network smoothing to both the healthy patients and schizophrenic patients in a study. And for each one, recover a kind of population brain, the average brain among all the healthy patients, the average brain among all of the schizophrenic patients. And then we can use some of these techniques to compare those two and say, for each region of interest, each chunk of brain, do these look the same in the schizophrenic patients and the healthy patients? That lets us identify what might it be that's going wrong physically in the brain of schizophrenics. Is there a structural correlate of schizophrenia? So I and some of my colleagues have started doing this. We've used some of these network smoothing ideas and these ideas behind embedding vertices into geometric space to smooth out this kind of noisy signal that we see in brain scans and identify what brain regions appear to be behaving differently in schizophrenic patients compared to healthy patients. Okay? So, for example, our method has identified two brain regions, or rather collections of brain regions, that we already know from prior studies are almost certainly implicated in schizophrenia. So these are the somatomotor cortex. So there are two stripes kind of going down the side of your brain that control your sensory inputs, or process your sensory inputs, and also move your extremities. Right? And that's known to be affected in schizophrenia. And then there's the default mode network. This is if you have someone just lie down in an MRI machine and just not think about anything, which is a weird thing to ask someone to do. But if you just, when you allow your mind to wander, there's a collection of brain regions that tend to light up and to consume a lot of oxygen. That collection of brain regions is called the default mode network. And again, it's known that this is altered in some way in schizophrenics. So our method, as this kind of, a kind of a sanity check. I don't mean to make that pun when we're talking about mental illness, but as a kind of sanity check, our method recovers these two known brain regions as being implicated in schizophrenia. So we have ongoing work in this line. Again, using these methods, the thing you want out the end is something like a p-value, another scary word that the statisticians use, but it's just a way of measuring how surprised should I be by the outcome that I saw in my experiment. And there's a lot of work here to be done to incorporate things like patient covariates, we say. So things like how old the patient is, their diet, exercise, genetic information, things like that. So ongoing work to incorporate that into this. But at a first order level, we have methods here that now allow us to start with this very complicated brain network data and make these region by region comparisons that account for the fact that these regions, the brain regions interact with one another. So with all of that, let me just recap. I hope that in the course of this short talk, I have managed to convince you that networks are everywhere, that they're worth studying because they have some rather striking properties. And hopefully I've shown you that they are not just some mathematical object that we like to stare at because they're pretty, but they actually have important uses for understanding things like the spread of disease, brain structure, things like that. I hope I've convinced you that networks are applicable in a broad array of scientific domains. Right? They show up in the social sciences, in economics, in neuroscience, in biology. Really, anywhere you look out there in the world, you're going to see a collection of things interacting. That's a network. And even more striking, we look at these networks from all these different domains, and we see a handful of phenomena repeat again and again. And understanding why that should be the case really is an open question. Finally, I hope I've driven home both that statistics for these objects is important, and it's still a very young field. I mean, I think if we're being charitable, this field of statistical network analysis is maybe 40 years old. So there's a lot of exciting new stuff to do. And the work that we're doing is really only becoming possible in the last 10 or so years as computing power and our ability to go out and collect lots of data has become possible. Because 20 years ago, we could not go out and collect all of the websites in the world and build a network on them. So with all of that, let me thank you for your time and attention, and thank, once again, Tom and all the people who run Wednesday night at the lab. It really is my pleasure to be here, and I'll be happy to take any questions. Thanks so much.
Questions?
Do I MC or does Tom?
You MC, I take the
All right, I think first hand was in the back, I'm afraid.
Okay. Here you go, Sandy.
Oh, my favorite kind.
More of a philosophical question about our response to the pandemic and the ignorance of network analysis.
Uh-oh.
In my own, I only was aware of Stanley Milgram's more famous experiment, and the other experimenter came to mind as Dunbar and the Dunbar number. So, but I think that the overall ignorance of your study, what effect does that have on our ill response to the pandemic? Poor response.
Oh boy. I almost want to plead the fifth here. Look, I don't know to what extent, what would are you asking sort of if the public knew more about network science, would we have done better? Epidemiologists. Or about I want to give the epidemiologists credit. There's actually a lot of work looking at how network structure influences the spread of disease. I am not an epidemiologist, and so I don't have a good sense of how well integrated that work is with the rest of the field. But I don't get the sense as though network science is some kind of ignored corner of science for them. I think I get the sense like they recognize it's important.
The public's ignorance of it. The epidemiologists did do a good job.
Yeah.
But they couldn't communicate that well. Science storytelling because of the ignorance.
It's hard though, right? Like I spent an embarrassing amount of time writing this talk. Communicating this stuff clearly to people who haven't done a bunch of math is hard. I don't know. It's easy to criticize the fact we could have done better in terms of science communication, but I don't know that I have. It's easy to criticize, but I don't know that I have the constructive criticism to give. It's hard. Like this starts at our education system. You can't. I don't know. The cake is baked by the time you're worrying about like explaining this kind of stuff to the public if they haven't seen this at least once before in their lives, right? I'm sorry, I don't have I'd like to. I'll be meaner over beers. How's that? That's a promise. Please.
Wait a second, Larry.
In the graphs that you were showing, they were all bidirectional. Is there a modeling that's done for directed graphs?
Yes, there's a lot, in fact. So the question concerns directed graphs. So so you caught the sneaky thing I did in this talk, which was to not even talk about directedness. But let's notice something. So I started this talk by talking about, way back here, social media. And I said a lot of words about Facebook and how certain pairs of users can be friends. And that friendship relation is symmetric. If I'm friends with you on Facebook, then by definition you are friends with me. Let's contrast that with Twitter. Technically speaking, on Twitter, the following relation is asymmetric. I may follow Tom on Twitter, but Tom need not follow me back. So sad.
But you don't have a Twitter account.
Because I don't have a Twitter account, but even if I did, yeah.
So I have a question real quick. How much effort did it take you not to include Ted in one of those 5 names?
A decent amount. It took some restraint. Right, so a complete answer to your question is that indeed we could, I think I just haven't fully answered that first question. Right, so you could make this directional, and
I don't know if you got
The answer is yes, we still have statistical models for those directional networks. They're actually a little more annoying to write down and do inference for, meaning actually produce p-values, but we can create them. Is a thing that exists. Another question?
So I work with people who do this type of work. I don't know it, but they do. So the interesting thing I think they were asking is essentially information flow, where there might be certain nodes that are more important than other nodes. And therefore, if you weighted those nodes, then you might be able to explain more real-world phenomena.
Yeah. Yeah, so one thing I didn't talk about much in this talk, but which is very important, is really diving into this picture. Like, there's not just a network, but there are processes that happen on it. So one of those processes could be disease spread, right? Again, maybe Carol gets sick. How long does it take for everyone in the network to get infected, right? How worried should we be if one of these people gets sick that the disease will spread to the whole network and we'll have a pandemic on our hands?
Or an infodemic.
Or an infodemic, exactly. So we could similarly think about information spreading over, say, the Facebook network or the Twitter network or something like that, right? And there, the same high-level ideas apply. Whatever it means to vaccinate someone against misinformation, you might want to find out who are the high-degree vertices, who are the people who spread a lot of information, and either prevent them from spreading misinformation or see to it that they're informed. This is something that I think about a lot and have yet to write anything because I'm terrified of getting it wrong. Like, getting this wrong would be catastrophic, right? So, but yeah, people more senior than I and smarter than I ought to work on this. Right? It's important.
Question from online. Sure. Is there any connection between network analysis and AI analysis? And artificial insemination is a big deal in Wisconsin.
I'm going to assume they meant artificial intelligence because I'm not in the School of Agriculture, and so I don't know much about artificial insemination. Sorry.
Welcome to Wisconsin.
Yeah. I'm still trying to get my head around the fact that we have like 5 different plant-related departments because we're historically an ag school. So the short answer is yes. So if you've heard of things like neural nets, right? Neural nets are supposed to vaguely approximate something like the structure of the brain. At least that was the original motivation for them. Now, if you say this kind of stuff to neuroscientists, you have to stop them from trying to fight you, because of course the structure of the brain is far more complicated than a neural net that we build. But you can, at a very high level, for studying things like visual cortex, you can kind of squint and argue why these structures should be analogous. More generally, the biggest connection here is actually with something called graphical models. This is a way of writing down, you have a collection of variables, and there's a way of writing down how those variables influence one another. So if we want to do things like causal analysis, figuring out, when we talk about controlling for things in a study, carefully writing down how confounding can happen, how it can be that, say, your study on education got messed up because you didn't control for, say, socioeconomic status. Right? Writing down these kinds of things involves writing down a directed network. So that's, I think, actually the nicest connection.
And Dareth is going to go through the 5 plant departments.
No, I'm
Is it
not.
more than 5? I made up the number 5. I don't actually know.
Well, you
how
were
many.
right. Botany,
Botany, plant pathology,
horticulture, agronomy, and the plant breeding program.
That's 5.
But are they
There are more?
Shh.
I don't know. Are they secretly all one department just wearing funny hats?
Hey.
That wasn't meant disparagingly. I genuinely don't know.
Okay. Any other questions?
In one of your early slides, you showed Connectomes as being controversial as one of the kinds of networks.
Yeah, so something that actually cut from this talk, and I'll talk about it for 30 seconds here. Some of these claims, there's more or less of a nerd fight going on over whether it's true. So you can find a few papers out there that are titled along the lines of like, Connectomes are not small world networks, or yes, they are, or there's a great nerd fight happening right now in the literature over, okay, you look at these kinds of plots in lots of different networks, you say, there's a power law, but like, is this a power law really? There's like, this part is a straight line, but this part isn't. A similar thing happens here. So there's a big fight over whether, how good an approximation is this and when is it appropriate, when isn't it? In the same way that the normal approximation is something that statisticians do all the time, but we know it's an approximation to reality, it's not the truth. So there's a big fight over kind of how good an approximation this is. And again, when we make claims like, oh, connectomes are small world networks. Well, are they really? What do we mean by that? Fleshing out the details is, of course, a controversial subject. So I put that there to be diplomatic towards people who will say like, well, not quite. And they're correct. You can always quibble with these things. They're approximations.
This is kind of similar to what you talked about before, but I mean, obviously, in like even the Facebook example or all these examples, there's a strength of that connection. There's some people you talk to a lot. There's some people you have as friends, but you never connect with. That strength must have a big influence on.
Yeah. So in fact, so once again, you've caught one of the gross simplifications I made. So just as I didn't really show you anything about the directionality of these edges, which can of course be there, these edges don't have to be just yes or no binary. They can be weighted, right? And in fact, that's kind of the motivation behind our smoothing ideas, right? These are weighted edges, right? The edges have a weight, say between 0 and 1 associated to them, that describes essentially, in this case, how confident are we that there's really an edge there in the true but unknown network. But you can extend this idea to say, so in fact, another gross simplification I made is that, man, I should have put these slides closer together. This is a weighted network, if you go and actually construct one or ask a neuroscientist for one. These edge weights are derived from correlations of what are called bold signals. So you, when someone lies down on an fMRI machine, what we're really doing is measuring what's called a bold signal, blood oxygen level dependent signal. It's a proxy for a proxy for a proxy, essentially. You're measuring, the physicists are going to get angry at me for getting this not exactly right. Something to do with the dipole moment of water. You like turn a magnet on and off really fast and the water molecules vibrate around, and you can somehow use that as a proxy for how much oxygen is being consumed at a point in the brain, which is itself supposed to be a proxy for how much brain activity is happening. You can see why there's this need to denoise these things, right? You measure that signal at different points in the brain, you measure the correlation between those signals, and that gives you a weight between those two vertices. That's that thing. Again, in a 45-minute general audience talk, these are the details that get left on the cutting room floor, but I'm glad you asked these questions, because it's important. Yes, yeah.
Could you elaborate on how the 80-20 principle applies to networks?
Yeah, so that 80-20 principle, so that's again this, the 80-20 principle is something like, so this is observed originally by an economist named Gini. There's a Gini coefficient, G-I-N-I. It describes an approximate. It's not as though every society out there you look and like, 80% of people own 20% of the wealth. That is a rule of thumb. 80% of people own, 20% of people own 80% of the wealth in many Western countries. This kind of 80-20 rule applies in lots of social systems. It's not just a wealth thing. In the case of degree, this would mean that 20% of vertices account for 80% of the total degree. And the total degree is just 2 times the number of edges, right? Every edge has 2 vertices. So if you look at, like, there's a total degree of 2 times the number of edges, 20% of the vertices account for 80% of that total degree.
Any other questions? If not, thank you very much. It's
Thank
great.
you so much, everyone. I really appreciate it. And thanks again to Tom and everyone who runs this every week. Really, this was like a bright spot in my life during the pandemic when, I had no idea who else was on campus or anything. So really, thank you.
Thank you very much for that. I appreciate it. It is part of building a community, which is another word for network, and it's a big part of why we do this, so I appreciate it.
Thanks so much. And thanks, everyone. Thanks for the great questions.
And then next week, we're going to have Reba Lucan from Horticulture, one of the 12 plant departments on
12
campus. We're doing a power law here thing. So thank you very much for coming, and then we're going to adjourn over to the library.